Hello there, and welcome to the Deep Space Science. I'm really glad you're here. Maybe your day has been long, or maybe you simply enjoy drifting off while thinking about galaxies, stars, and the mysteries that lie far beyond our tiny world. Whatever brought you here tonight, this moment is yours. You don't need to do anything at all. Just rest. Let your thoughts soften, let your breathing settle into a calm rhythm, and let your body feel as though the pull of gravity has gently loosened its hold. Tonight, we're heading far beyond the familiar sky into the quiet, endless ocean of deep space, and you're invited to drift along with it. In the quiet darkness beyond our night sky, a great companion drifts slowly toward us, a vast and ancient spiral galaxy whose light has traveled more than 2 million years to reach our world. This is the Andromeda Galaxy, the closest giant neighbor to the Milky Way, a colossal city of 1 trillion stars spread across a disk so wide that it would take light itself hundreds of thousands of years to cross from one side to the other. If you step outside on a clear night and gaze toward the constellation of Andromeda, you might notice a faint misty blur, barely brighter than a whisper against the sky, yet it is one of the most distant objects visible to the naked eye. That delicate smudge is a universe unto itself, filled with ancient suns, swirling arms, drifting worlds, and mysteries shaped over cosmic epochs. As Andromeda drifts toward us through the dark, guided only by gravity and time, it carries with it the story of countless stars that lived and died long before Earth even formed. Its motion is slow on human scales, so slow you could watch the sky for an entire lifetime and never notice a difference, but steadfast on cosmic scales, drawing our galaxies ever closer. Tonight, we allow our minds to drift toward this distant companion, imagining its bright core, its glowing arms, and the silent interstellar spaces between its stars. We picture the vastness of its dust lanes, the quiet pulse of its star-forming regions, and the old red giants that shine like embers in the dark. As we travel there with thought alone, we become part of a larger story, one in which two great galaxies move toward an eventual meeting, not with violence, but with slow, graceful transformations spread across billions of years. The Andromeda Galaxy is not just a point of light in the sky, it is a reminder of the immensity that surrounds us, the calm drift of cosmic structures, and the deep time through which everything evolves. And as we rest beneath the stars, we share the same universe that Andromeda illuminates, one where light travels vast distances, where galaxies wander through the dark, and where we, on our small planet, can look up and feel the quiet pull of a cosmic neighbor drawing ever closer. The Andromeda Galaxy, often known as M31, is a sprawling, majestic spiral galaxy whose scale challenges our ability to imagine size at all. When we describe it as more than 220,000 light-years across, the number feels almost abstract, yet each light-year represents nearly 10 trillion kilometers of distance. Stretch that across hundreds of thousands of light-years, and you begin to sense the vastness of this rotating island of stars. Andromeda's structure is a classic example of a barred spiral galaxy, with sweeping arms that coil outward from a bright, dense core. These arms are made not only of stars, but also of colossal clouds of gas and dust, the raw material from which new suns and planetary systems emerge. When astronomers look at Andromeda in different wavelengths, from ultraviolet to infrared, they see a galaxy layered with activity, rings of star formation, arcs of glowing hydrogen, and dark dust lanes that cut gently across its luminous disk. At its heart lies a dense central bulge composed of older stars, many of them red giants that have burned for billions of years. This bulge is elongated, forming a bar-like structure whose gravitational influence shapes the inner regions of the galaxy. Surrounding the disk is an enormous halo, a vast, incredibly diffuse sphere that extends far beyond the visible arms. It contains ancient stars, star clusters, and remnants of smaller galaxies that Andromeda once consumed. Although the halo appears faint in visible light, it holds clues to Andromeda's earliest history, preserving evidence of collisions and mergers that helped build its current form. The spiral arms themselves are not rigid structures but patterns created by density waves, regions where gas and dust become slightly compressed, triggering bursts of star formation. When we see bright blue stars tracing these arcs, we are witnessing the locations where stellar nurseries have recently been active. These young, massive stars burn brilliantly but briefly, living only millions of years before fading or exploding as supernovae. Meanwhile, older stars drift in and out of the arms, moving according to the galaxy's rotation and local gravitational influences. Andromeda's rotation curve, how quickly stars orbit at different distances from the center, reveals that the galaxy is dominated not by visible matter, but by dark matter. Without a huge, unseen halo of this mysterious substance, the galaxy's outer regions would not rotate as fast as they do. Dark matter's gravitational pull holds Andromeda together, binding its limbs, stabilizing its structure and shaping its evolution. From afar, Andromeda appears symmetrical and serene, but closer analysis shows subtle asymmetries. One side of the disk is thicker, spiral arms differ in brightness, and ring-like features ripple through the structure like echoes of past events. These irregularities hint at interactions with smaller galaxies, which tug on Andromeda's disk and stir its stars. Even now, traces of these encounters remain visible, embedded in the galaxy's shape. To describe Andromeda's size and structure is to describe a living cosmic system, one shaped by gravity, enriched by star birth and death, and stretched across distances so immense that light takes ages to cross them. It is not a static picture, but an evolving, rotating, breathing architecture of matter and energy, a spiral of time and space turning silently through the deep dark. The Andromeda Galaxy contains an astonishing number of stars, far more than the Milky Way, and each one contributes to the immense glow that travels across 2 million light-years to reach us. Estimates suggest that Andromeda may host close to 1 trillion stars, a number so vast that even imagining it feels like staring into infinity. Every star within that immense collection has its own life story. Some are enormous blue giants blazing with fierce intensity, living fast and dying young. Others are small, cool red dwarfs that could burn quietly for hundreds of billions of years, outliving the galaxy as we know it. Many of Andromeda's stars orbit within the grand spiral arms, forming broad lanes of light that curve gracefully around the galaxy's center. These spiraling structures are shaped by density waves, gentle compressions in the galactic disk that trigger bursts of star formation. When gas clouds encounter one of these waves, gravity pulls the material together more tightly, giving birth to clusters of new stars. These newborns shine with a brilliant blue hue, illuminating the arms and making them prominent against the darker background of space. Andromeda's inner regions are dominated by older stars, dense and glowing softly. Many of these ancient suns have burned for billions of years, evolving slowly and drifting in patterns influenced by the galaxy's central bar. That bar is a feature shared by many spiral galaxies, including the Milky Way, where the mass of stars arranges itself into an elongated shape that rotates as a single unit. This bar directs gas inward, fueling star formation near the core and feeding the supermassive black hole that lies at the very center. Surrounding the disk is Andromeda's massive stellar halo, a vast and nearly invisible region populated by extremely old stars. Some are as ancient as the earliest epochs of galaxy formation. These distant halo stars orbit the galaxy at great distances, following long, slow paths shaped by the gravitational pull of dark matter. Within the halo are also globular clusters, tight spheres of hundreds of thousands of stars bound together with remarkable stability. Andromeda holds far more of these clusters than the Milky Way, adding to the evidence that it has experienced numerous mergers with smaller galaxies over its long life. These mergers not only increase the number of stars in Andromeda, but also enrich the chemical complexity of its stellar population. The sheer number of stars in the galaxy means that Andromeda contains countless possible planetary systems. Given its trillion suns, the chances of worlds forming around many of them are extremely high. Some may be barren and cold, while others might orbit in gentle habitable zones, warmed by the steady glow of their host stars. We cannot see these planets with the naked eye, and only a handful might ever be detected directly, but the probability of their existence is enormous. Imagining Andromeda's star population is like imagining an entire ocean made of light. Each point within that shining expanse represents a sun. Each sun may hold planets, and each planet could contain environments as diverse and surprising as those found in our own galaxy. When we see Andromeda as a faint blur in the sky, we are witnessing the combined glow of 1 trillion distant fires, a soft, ancient radiance from a galaxy packed with stars that will continue to burn long after we are gone. The Andromeda Galaxy holds a commanding place within the local group, the small community of galaxies that share a common gravitational landscape with the Milky Way. While space between galaxies is immense and seemingly empty, gravity binds these members together in a slow, ancient dance that has lasted billions of years and will continue for billions more. The local group contains more than 50 galaxies, most of them small dwarfs barely visible even through powerful telescopes. But at its heart stand two giants, the Milky Way and Andromeda. These two massive spirals dominate the entire structure, shaping the motions, orbits, and destinies of the smaller galaxies around them. Andromeda, slightly larger and more massive than the Milky Way, exerts a strong gravitational pull that influences its neighbors in subtle but unmistakable ways. When we imagine the local group, we often picture a kind of cosmic archipelago, a collection of islands drifting in a dark sea. Andromeda is one of the largest islands, shining with the light of 1 trillion stars. Just as the Milky Way has its family of small satellite galaxies, the Large Magellanic Cloud, the Small Magellanic Cloud, and others, Andromeda has its own entourage. Two of its most famous companions are M32 and M110, small elliptical dwarf galaxies that orbit close to Andromeda's glowing disk. Their shapes and motions reveal that they have interacted with Andromeda many times, possibly losing stars and material through tidal forces as they passed near its massive gravitational field. Surrounding these lie dozens of even fainter satellites, some no larger than star clusters, their stars so sparse that they are difficult to distinguish from the background of space. The local group is not arranged like a tidy map with clear borders. Instead, it is a gravitational territory, defined by the region where the pull of Andromeda and the Milky Way dominates over the expansion of the universe. Within this volume of space, galaxies move not outward with cosmic expansion, but inward toward one another, guided by mutual attraction. Andromeda and the Milky Way are the primary centers of gravity in this region, shaping the motions of smaller members like Triangulum, M33, the third largest galaxy in the group. M33 orbits loosely around Andromeda and may be gravitationally bound to it, though astronomers continue to refine these measurements with ever-improving data. The interactions among the local group's galaxies leave visible traces. Streams of stars arc through space, marking the remains of small galaxies torn apart by tidal forces. Clouds of gas stretch between members, hinting at past collisions or near passes. Dark matter halos overlap and blend at their edges, revealing a deeper, invisible structure that threads through the entire group. Andromeda's role in this cosmic community is both that of a leader and a participant. It is massive enough to shape its surroundings, yet it too feels the pull of the Milky Way. Their mutual attraction sets the stage for their future merger, which will ultimately reshape the local group into a new, larger galaxy. To understand the local group is to understand that Andromeda lives not in isolation, but as part of a gravitational family. Its presence influences the movements, shapes, and histories of dozens of smaller galaxies, and together they form a quiet cluster drifting through the vastness of intergalactic space, held together by forces older than stars themselves. Andromeda is not drifting randomly through space. It is moving directly toward the Milky Way at a speed of about 110 kilometers per second, a steady, unstoppable glide shaped by the invisible pull of gravity. This motion has been measured with remarkable precision thanks to decades of observations, beginning with the detection of a blue shift in Andromeda's light. While most galaxies in the universe are redshifted moving away from us as space expands, Andromeda is one of the rare large galaxies that is blue shifted, meaning its light waves are compressed as it approaches. This single fact was the first clue that our galaxies are on a collision course, one that will eventually transform both into something entirely new. The speed at which Andromeda moves toward us may seem fast by human standards, but on cosmic scales, it is gentle and unhurried. At 110 kilometers per second, it would take more than 4 billion years before the galaxies meet, giving stars, planets, and even entire stellar populations time to rise, evolve, and fade away before the encounter begins. Although the idea of a collision sounds dramatic, the reality is far more graceful. Stars are spaced so widely that direct impacts between them are extremely unlikely. Instead, the collision will reshape the galaxies, stretching their spiral arms, distorting their disks, and sending waves of star formation through their gas clouds as gravitational tides pull and twist their structures. Understanding Andromeda's motion has been a long scientific journey. Early measurements in the 20th century could only detect its approach along our line of sight, but astronomers did not know whether Andromeda also had a sideways or tangential motion that could change its trajectory. If Andromeda were drifting sideways as much as it approached, the galaxies might have missed each other entirely and merely passed by. But as instruments improved, especially with the extraordinary precision of the Hubble Space Telescope and later the Gaia spacecraft, astronomers were able to measure Andromeda's proper motion with enough accuracy to confirm that it is indeed heading directly toward us, not skimming past. Its path is set, determined by gravitational attraction between two galaxies, whose combined mass outweighs everything else in the local group. Another surprising detail is that Andromeda's dark matter halo already overlaps with the Milky Way's halo. These enormous invisible spheres of mass extend far beyond the visible disks of both galaxies, meaning the outer edges of our galaxies are already interacting subtly. Over time, these halos will continue to draw the galaxies closer, accelerating their approach ever so slightly. Even now, the gravitational influence between the Milky Way and Andromeda shapes the motions of smaller galaxies around them, guiding their orbits and slowly rearranging the architecture of the local group. When we think about Andromeda moving toward us, we often picture a distant blur creeping across the sky, but the scale of its motion is far beyond human perception. It will take millions of years for its position to shift even slightly against the background of stars. Yet the journey continues, step by step, second by second, as two great spirals drift toward a future where they will meet, merge, and create a new galaxy. It is a reminder that even across unimaginable distances, gravity acts with patience and certainty, shaping the fate of stars, planets, and galaxies over the longest spans of time. The future collision between the Milky Way and the Andromeda Galaxy is one of the most majestic events awaiting our corner of the universe, a cosmic transformation so immense that it will reshape the local group and create an entirely new galactic form. Although the word collision evokes images of chaos and destruction, the reality is both gentler and more elegant. When Andromeda finally arrives in roughly 4 to 5 billion years, the encounter will unfold slowly, over billions of years, in a sequence of gravitational interactions more like a celestial dance than a violent crash. The first approach will stretch and distort both galaxies. As their halos overlap more fully, long before their disks touch, gravitational tides will begin pulling stars into sweeping arcs. These tidal tails will extend across hundreds of thousands of light years, forming luminous ribbons of starlight that mark the early stages of merging. When Andromeda's disk finally intersects with the Milky Way's, stars from both galaxies will pass through one another, like interwoven streams of light. Direct star-on-star collisions will be extremely rare because the distances between stars are vast, but their mutual gravity will rearrange their orbits, sending some stars into elongated paths, flinging others into the halo, and causing yet others to fall toward the central regions. Clouds of gas, however, will collide more directly. When massive gas clouds strike one another, they compress violently, triggering bursts of star formation far greater than what either galaxy currently produces. These brilliant newborn stars will ignite in clusters, and supernovae will follow in their wake, enriching the surrounding space with heavy elements. The night sky on any surviving planets will glow with new star-forming regions shining like cosmic lanterns. After the first pass, the galaxies will not merge immediately. They will swing past each other, slow down, and be pulled back together by gravity. This oscillation may happen several times, each pass drawing the galaxies closer, stretching their disks and mixing their stars until their original shapes are no longer recognizable. Over time, their spiral structures will dissolve, and the two central regions will drift inward, slowly spiraling until they combine. At the heart of the new system, the supermassive black holes from both galaxies will eventually find each other, orbiting in tightening loops until they finally merge. This event will unleash powerful gravitational waves that ripple across space, though by then humanity will likely be long gone or transformed beyond recognition. The final result will not be a spiral galaxy, but a giant elliptical or lenticular galaxy, often referred to as Milkdromeda or Milkomeda. It will be larger, rounder, and far more massive than either galaxy is today. The star formation rate will eventually decline as gas is consumed or heated, leaving behind a calmer, older population of stars. Any surviving solar systems, including our own if it still exists, may find themselves flung into new orbits far from their original homes. The Sun itself will no longer be alive, having passed into its red giant and white dwarf phases long before. Yet the stars that remain will orbit peacefully within the new galaxy, bound together by gravity in the silent aftermath of a cosmic union billions of years in the making. The collision between the Milky Way and Andromeda is not a catastrophe, but a renewal, the natural evolution of large galaxies as they age. It is a reminder that even on the largest scale, the universe is always changing, always transforming, shaping new structures from old ones in a slow, beautiful choreography written across cosmic time. Andromeda's past is written not only in the stars we see today, but also in the faint, stretched remnants of galaxies it consumed long before humanity ever looked toward the sky. Like the Milky Way, Andromeda did not form in isolation. It grew through a long sequence of mergers and collisions with smaller galaxies, each interaction leaving behind subtle distortions, ripples, and streams that still trace the outlines of ancient events. The story of Andromeda is a story of cosmic cannibalism, of a giant spiral built from the remnants of many smaller systems whose individual identities have long since been absorbed into the larger whole. One of the clearest pieces of evidence for Andromeda's dramatic past is the presence of massive stellar streams encircling it, long ghost-like trails of stars that stretch far beyond the bright disk. These streams are the shredded remains of dwarf galaxies, torn apart by Andromeda's gravity. As they spiraled inward, stars were pulled off in graceful arcs, creating loops and ribbons that now orbit the galaxy like pale echoes. Some of these streams form loops hundreds of thousands of light years long, indicating that the mergers happened over long, extended periods and involved multiple passes before the smaller galaxies finally dissolved. Recent studies also show that Andromeda underwent at least one major merger in the past few billion years, possibly a collision with a galaxy nearly 1/4 its size. Such an event would have dramatically reshaped Andromeda's structure, potentially triggering waves of star formation and altering the distribution of stars in its disk and halo. These interactions may explain some of Andromeda's unusual features, such as its thickened disk, its off-centered rings, and certain asymmetries in its spiral arms. Evidence suggests that Andromeda's halo is far more complex than previously believed. Instead of being a smooth, spherical region of ancient stars, it is filled with clumps, shells, and substructures, each a signature of a past encounter. Some halo stars move in synchronized patterns as though they once belonged to the same small galaxy before being scattered. Others carry distinctive chemical fingerprints, with metal pore compositions that hint at origins in primitive dwarf galaxies from earlier epochs. One of the most striking discoveries is that Andromeda's halo is populated by stars that are strikingly similar in age and metallicity, suggesting a massive merger event dominated its recent past. It is possible that this single large collision shaped the galaxy's current form more than any other event. Even Andromeda's globular cluster's ancient, tightly bound groups of stars tell a story of mergers. Many clusters orbit in unusual paths, tilted or elongated compared to the main disk, indicating they were brought in by swallowed galaxies. Some clusters appear unusually metal-poor or metal-rich for their positions, hinting that they formed elsewhere and were later adopted into Andromeda's vast family. The galaxy's central region also bears marks of past interactions. The double nucleus 2, bright clusters near the core, may have originated from the merger of a smaller galaxy, whose core survived long enough to sink inward and remain as a distinct structure. In this way, even the heart of Andromeda carries the memory of its past. When we look at Andromeda today, we are not seeing a pristine spiral formed from a single collapse of gas and dust. We are seeing a layered tapestry woven from the remains of dozens of smaller galaxies, each one contributing stars, clusters and streams to the luminous giant we observe. Andromeda's past is turbulent, rich and essential to understanding how galaxies grow, not through quiet evolution, but through the slow, majestic merging of countless worlds over cosmic time. Surrounding the luminous disk of the Andromeda Galaxy lies one of its most mysterious and awe-inspiring features, a vast, stellar halo, so large and diffuse that it stretches far beyond what the human eye, or even many telescopes, can detect. This halo is not a simple empty shell. It is a sprawling spherical realm of ancient stars, dark matter, globular clusters, and tidal debris from long-forgotten galactic mergers. If the bright disk of Andromeda is its visible body, then the halo is its ghostly atmosphere, a faint and ancient sphere that contains crucial clues about the galaxy's formation history. One of the most striking characteristics of Andromeda's halo is its enormous extent. Recent observations show that it reaches more than 1 million light-years from side to side, comparable in size to the halo of the Milky Way, and large enough that the outer fringes of both galaxies' halos already overlap. This means that, on the deepest level, the Milky Way and Andromeda are already touching, their dark matter envelopes blending in the quiet darkness of intergalactic space, long before their luminous parts collide. The halo is populated by extremely old stars, many of them metal-poor survivors from the earliest epochs of galaxy formation. Some were born in dwarf galaxies long since consumed by Andromeda, their stars now scattered across the halo in faint, loosely bound orbits. These stars often move in distinct streams or clumps, evidence that their original galaxies were torn apart gradually over billions of years. When astronomers map the halo, they find arcs, shells, and intricate substructures, cosmic fingerprints of past interactions that reveal Andromeda's dynamic history as a galactic cannibal. Among the most remarkable features in the halo are its numerous globular clusters. Andromeda contains far more globular clusters than the Milky Way, and many reside far from the galactic disk, orbiting independently through the halo's deep gravitational field. Their ages suggest that some formed more than 12 billion years ago, while others were likely captured during mergers. Their distribution and composition offer one of the clearest windows into the galaxy's violent past. The halo is also where dark matter plays its most dominant and enigmatic role. Although invisible, dark matter outweighs the luminous parts of the galaxy many times over, forming a massive underlying framework that shapes Andromeda's rotation, structure, and evolution. Without this dark matter halo, the galaxy's outer stars would not orbit fast enough to remain gravitationally bound. Instead, they would drift into space. The presence of dark matter is inferred through these unexpectedly high orbital velocities, particularly in the fringe regions far from the central disk. But the halo is not made only of stars and dark matter. It also contains hot, diffuse gas that extends far beyond the visible galaxy. This gas, heated by supernovae and the galaxy's gravitational collapse, glows faintly in ultraviolet and X-ray wavelengths. Observations reveal that this hot halo may contain as much mass in gas as all the stars in the galaxy combined. It forms a cosmic reservoir from which Andromeda can potentially draw new material to fuel future star formation. Yet the halo is extraordinarily thin compared to the disk, so thin that even if you could travel through it in a spaceship, you would find it emptier than the best vacuum humans can create. And still, within that near nothingness, the history of entire galaxies is preserved. Looking at Andromeda's halo is like reading the ghost record of cosmic time. Every stream of stars, every isolated cluster, and every faint glow of gas tells a story of formation, destruction, and assimilation. It is within this vast halo quiet, ancient and nearly invisible, that Andromeda's deepest secrets hide, waiting to be uncovered by the next generation of astronomers. Orbiting around the Andromeda Galaxy is a rich collection of satellite galaxies, each one a smaller companion pulled into Andromeda's vast gravitational sphere over billions of years. These satellites are not merely decorative features but active participants in Andromeda's story, shaping its evolution and being shaped by it in return. Some are compact, dense, and bright, while others are faint, ghost-like systems barely distinguishable from the surrounding darkness. Together, they form an extended family of galaxies, each with its own history, structure, and relationship to Andromeda. Two of the most famous satellites are M32 and M110. These small elliptical galaxies orbit close to Andromeda's bright disk and have been studied for more than a century. M32 in particular is unusually compact and bright, leading astronomers to suspect that it might once have been a much larger galaxy, stripped of its outer layers through tidal interactions with Andromeda. Its remaining core shines with densely packed stars, giving clues about what kinds of galaxies Andromeda has absorbed. M110, by contrast, is more diffuse and elongated, with signs of recent star formation that suggest it still retains some gas, an unusual feature for a dwarf elliptical. Beyond these well-known companions lie dozens of dwarf spheroidal and dwarf irregular galaxies scattered across the region surrounding Andromeda. Many are incredibly faint. Their stars spread so thinly that they resemble mere smudges, even in deep astronomical images. Some contain only a few million stars, a tiny population compared to the trillion housed within Andromeda itself. These galaxies often contain little to no gas, having lost it either to internal processes or to the stripping effects of Andromeda's gravitational pull. The arrangement of these satellites is not random. Observations have revealed that many of Andromeda's companions lie in a vast, thin plane that stretches across the galaxy, almost like a cosmic disk of dwarf galaxies floating around the main spiral. This unexpected structure has puzzled astronomers, as it suggests a level of order in the distribution of satellites that contradicts some predictions of dark matter models. It raises questions about whether Andromeda experienced a coherent infall of satellite galaxies long ago, or whether another mechanism arranged them so neatly. Interactions between Andromeda and its satellites leave subtle yet profound marks. Some dwarf galaxies show signs of being stretched by tidal forces, their shapes elongated as though pulled apart. Others leave behind stellar streams-long trails of stars that peel away from the galaxy as it orbits too close to Andromeda's gravity. These streams eventually blend into the halo, becoming part of the larger tapestry of Andromeda's past mergers. One of the most intriguing satellites is the Triangulum Galaxy, or M33, the third largest member of the local group. Although much smaller than Andromeda, M33 is a full spiral galaxy in its own right, with bright star-forming regions and a well-defined structure. Some studies suggest that M33 may be gravitationally bound to Andromeda, orbiting it in a vast looping path. If this is true, past interactions between the two spirals may have triggered bursts of star formation or altered their structures. There is even speculation that M33 could eventually merge with Andromeda, before or during the larger merger with the Milky Way. Andromeda's satellite system is also rich in globular clusters that orbit far from the central disk, some of which may once have been the cores of dwarf galaxies stripped of their stars. These clusters provide additional clues about Andromeda's long history of galactic interactions. The satellite galaxies of Andromeda form a dynamic, evolving ecosystem of stellar systems. Each one, whether large like M33 or nearly invisible like faint dwarf spheroidals, contributes a piece to Andromeda's story. Together, they represent the ongoing process of galactic growth, a quiet but relentless shaping of the universe, where even the smallest galaxies leave lasting imprints on the giants they accompany. At the heart of Andromeda's structure and motion lies one of the greatest mysteries in astrophysics, the profound influence of dark matter. Although we cannot see it directly, dark matter shapes the galaxy's behavior in unmistakable ways, holding its vast disk together and sculpting the orbits of billions of stars. Without dark matter, Andromeda as we know it simply could not exist. Its visible matter alone is far too light to account for the galaxy's high rotation speeds. When astronomers measure how fast stars orbit within Andromeda, they find something surprising. Near the center, stars rotate quickly as expected, but farther out, instead of slowing down, their speeds remain almost constant, defying the predictions of Newtonian physics if only visible matter were present. This phenomenon, known as the flat rotation curve, reveals the presence of a massive halo of invisible material surrounding the galaxy. Dark matter is not a minor component. It makes up the majority of Andromeda's mass, outweighing all its stars, gas, and dust many times over. This invisible halo extends far beyond the luminous disk, so far that it overlaps with the Milky Way's own dark matter halo, forming an enormous gravitational bridge between the two galaxies. This connection means that the galaxies are already interacting on a deep level, drawn toward each other by a shared envelope of unseen mass. The structure of Andromeda's dark matter halo is not uniform. Observations suggest that it is lumpy and asymmetric, with clumps and subhalos scattered throughout. These irregularities are likely remnants of smaller galaxies that were incorporated into Andromeda long ago. As dwarf galaxies fell in, dark matter from their halos merged with Andromeda's, leaving behind subtle distortions like dents in an ancient landscape. These substructures help astronomers reconstruct the galaxy's past, revealing how frequently it merged with other systems and how those encounters unfolded. Dark matter also shapes the orbits of the satellite galaxies surrounding Andromeda. The motions of dwarf galaxies like M32, M110, and many faint spheroidals can only be explained if they are embedded within and influenced by a massive, extended halo. Even the thin planar arrangement of satellites, a puzzling feature that challenges some cosmological models, may be linked to how dark matter clumps guide incoming systems along preferred paths. Beyond shaping the galaxy's gravitational environment, dark matter influences Andromeda's long-term evolution. It stabilizes the disk, prevents stars from flying outward, and governs how material flows within the galaxy. Without its gravitational pull, spiral arms would warp beyond recognition, and the galaxy's outer regions would disperse into space. Some theories even suggest that the distribution of dark matter may influence the formation of the central bar, helping to determine the structure of the galaxy's core. Yet despite its essential role, the true nature of dark matter remains unknown. It does not emit light, absorb it, or interact with normal matter except through gravity. It passes through stars and planets without friction, invisible and silent. Scientists have proposed many possibilities, from exotic particles to yet undiscovered physical laws, but none have been proven. And so, Andromeda, like every large galaxy, is both a beacon of light and a shadow of mystery. It glows brightly with the radiance of 1 trillion stars, but it exists within a massive, invisible skeleton that defines its shape, motion, and destiny. Dark matter holds Andromeda together, guides its satellites, and draws it ever closer to the Milky Way. It is the unseen architect of the galaxy's past and the quiet sculptor of its future, a reminder that most of the universe's mass lies beyond the reach of our eyes, waiting for us to uncover its secrets. At the very center of the Andromeda Galaxy lies a region of extraordinary complexity, where gravity, light, and motion intertwine to create one of the most intriguing galactic cores in the universe. This central zone is dominated by a supermassive black hole, a gravitational titan millions of times more massive than the Sun. Yet Andromeda's core is far from simple. It contains structures, star clusters, and motions that reveal a past shaped by mergers, tidal forces, and ancient bursts of activity, making it one of the most unusual galactic nuclei ever studied. The supermassive black hole at Andromeda's center is estimated to be about 100 million solar masses, significantly larger than the Milky Way's Sagittarius A. Despite its immense mass, the black hole is currently quiet, not actively feeding in a way that would make it a brilliant quasar. Instead, it sits at the heart of a dense region of stars, embedded within an elongated structure known as the double nucleus. Andromeda's double nucleus is one of its most distinctive and puzzling features. When astronomers observed the core in high resolution, they discovered not one but two bright, compact star clusters extremely close together. These clusters, known as P1 and P2, appear almost like two luminous knots orbiting a shared center. One explanation is that P2 marks the true location of the supermassive black hole, while P1 is a cluster of stars whose orbit has been stretched out into an elongated disk by the intense gravity of the core. This strange configuration creates the illusion of two separate nuclei, even though both structures are part of the same gravitational system. The stars near the core move at incredible speeds, whipping around the central black hole in tight, fast orbits. Their motion is one of the clearest indicators of the black hole's enormous mass. The gravitational influence of this central region extends far beyond the immediate surroundings, shaping the flow of gas and stars throughout the galaxy's inner bulge. Observations reveal that Andromeda's inner bulge is not symmetrical. It has a barred structure, an elongated shape formed from stars orbiting on organized, stable paths. This bar likely plays a role in channeling gas toward the central regions, feeding star formation or occasionally allowing material to fall toward the black hole. The bar also helps explain the galaxy's spiral pattern, linking the core to the larger disk. Andromeda's inner regions also show signs of past violence. There is evidence that the central black hole may have once been far more active, perhaps even shining as a quasar long ago. Enormous jets or energetic outflows from such a phase could have shaped the distribution of gas, leaving behind cavities or high-energy structures that are still faintly visible in certain wavelengths. Some studies suggest that the double nucleus could have been formed by the merger of a smaller galaxy, whose core managed to survive long enough to sink toward Andromeda's center, leaving behind a distinct cluster. The black hole at Andromeda's core may also merge with another supermassive black hole in the distant future, either from this past event or from the eventual collision with the Milky Way. Such mergers produce gravitational waves that ripple through space-time, marking one of the universe's most powerful but silent events. Despite its complexity, Andromeda's core is surprisingly dim in visible light compared to active galactic nuclei. It is a relatively calm region today, though packed with stars so densely that they form one of the most crowded environments in the local group. Within just a few light years, millions of stars orbit the black hole, creating an intense but quiet brilliance. The center of the Andromeda Galaxy is a place where time, gravity, and history converge. It is a relic of ancient collisions, a home to one of the most massive black holes nearby, and a dynamic engine that shapes the galaxy's spiral arms and inner structure. To peer into this core is to see both power and stillness, a region where the universe's most extreme forces have sculpted a luminous heart that beats slowly in the dark of intergalactic space. Star formation within the Andromeda Galaxy is a dynamic process shaped by the movement of gas, the structure of its spiral arms, and the remnants of past collisions that continue to influence its vast disk. Although Andromeda is often described as being slightly less active in forming new stars than the Milky Way, the galaxy is far from dormant. It contains sprawling regions of molecular clouds, glowing nebulae, and pockets of intense stellar birth where gravity gathers gas into dense clumps that eventually ignite into new suns. These star-forming regions are most prominent along Andromeda's spiral arms, where density waves compress the interstellar medium. When a gas cloud drifts into one of these waves, it feels a gentle squeeze that causes its material to collapse inward. As the gas becomes denser, it cools and fragments, with each fragment collapsing under gravity to form a protostar. Over time, these protostars heat up, spin faster, and eventually undergo nuclear fusion, becoming fully formed stars whose radiation illuminates the surrounding clouds. The brightest and most energetic of these newborn stars are hot, massive blue stars, which shine intensely but live short lives. Their ultraviolet radiation ionizes the surrounding hydrogen gas, creating large, glowing nebulae that trace the outlines of the spiral arms. These stellar nurseries are like galactic beacons, revealing where new generations of stars are being born. One of Andromeda's most intriguing features is a large, ring-like structure of star formation located slightly off-center within the disk. This ring is believed to be the result of a past collision, possibly with the satellite galaxy M32. When a smaller galaxy plunges through a larger one, it can send gravitational ripples outward, compressing gas into ring shapes and triggering waves of star formation that can persist for hundreds of millions of years. The presence of this ring is a sign that Andromeda's star-forming activity has been shaped not only by its internal structure, but by its interactions with smaller companions. The inner regions of Andromeda, by contrast, are dominated by older stars and show far less star formation. Near the galactic center, the gas has largely been consumed, heated, or expelled, leaving behind a population of mature stars that glow more softly. Still, isolated pockets of gas occasionally ignite into new stars, adding to the complex layers of stellar generations within the bulge. Andromeda's outer disk also contains significant star-forming activity, particularly where gas remains relatively cold and undisturbed. Here, large molecular clouds drift through the quiet outskirts, giving rise to clusters of stars that orbit far from the bustling center. These outer regions hold immense reservoirs of hydrogen gas, some of which may fuel future star formation for billions of years as the galaxy continues its slow evolution. Supernovae, the explosive deaths of massive stars, play a crucial role in shaping star formation throughout Andromeda. When a massive star collapses and detonates, it sends shockwaves through the surrounding interstellar medium. These shockwaves can compress nearby clouds, initiating new rounds of starbirth. At the same time, supernovae inject heavy elements such as carbon, oxygen, and iron into the galaxy, enriching the material from which new stars and planets will form. Over billions of years, this enrichment process has transformed the chemical makeup of Andromeda, turning it from a primordial system of simple elements into a mature galaxy filled with complex chemistry. Although Andromeda's rate of star formation is somewhat lower than the Milky Way's, it still produces new stars at a steady pace. Estimates suggest that Andromeda forms roughly one solar mass of stars per year, a gentle but persistent contribution to its vast stellar population. The galaxy appears to be transitioning toward a quieter phase of its life, with declining star formation compared to earlier epochs. Yet the galaxy remains alive with activity, shaped by the ongoing cycle of gas collapse, stellar birth, supernova death, and chemical renewal. Star formation in Andromeda is not merely a process. It is the heartbeat of the galaxy, a continuous rhythm of creation and transformation that has persisted for billions of years and will continue as long as the galaxy holds enough gas to give birth to new stars. The spiral arms of the Andromeda Galaxy form some of its most defining and visually striking features, sweeping across the galactic disk in long, luminous arcs carved by the interplay of gravity, rotation, and interstellar matter. Although they appear as solid structures when viewed in images, the arms are not fixed formations of stars, but rather shifting waves of density that move through the galaxy over millions of years. These density waves act like gentle traffic jams, slowing and compressing gas clouds as they pass, triggering bursts of star formation that light up the arms with clusters of brilliant young stars. Because these newborn stars burn hot and bright, especially the massive blue ones, they highlight the spiral patterns, even though stars themselves drift in and out of the arms over time. This creates the illusion of permanent structure within a constantly moving system. Andromeda's spiral arms are not perfectly symmetrical. In fact, one of the most intriguing aspects of the galaxy is the irregularity of its arm structure, with some arms appearing fragmented, offset, or split into smaller segments. This asymmetry suggests that Andromeda's past interactions with satellite galaxies have significantly influenced its shape. When dwarf galaxies pass near or through the disk, their gravitational pull can disturb stars and gas, bending or twisting the arms in subtle but lasting ways. These disturbances can take millions of years to settle, leaving behind patterns that reveal events long past. One particularly unusual feature of Andromeda is its prominent ring-like structure located within the disk. While it resembles a spiral arm, evidence suggests it may have formed when a smaller galaxy passed directly through Andromeda's center, sending waves of compression outward like ripples on a pond. These ripples triggered widespread star formation along their expanding fronts, giving rise to a ring of young, bright stars. This ring is slightly off-center, another clue that it resulted from a collision rather than from the galaxy's regular spiral pattern. In addition to the main arms, Andromeda contains regions where the arms appear to fork or twist, creating complex shapes that reflect the dynamic forces shaping the disk. Radio and infrared observations show that the arms contain dense clouds of molecular hydrogen massive reservoirs of raw material for new stars. Dust lanes also weave through the arms, obscuring starlight in visible wavelengths, but glowing faintly in infrared. These dust lanes trace the densest parts of the arms, marking where gas is most likely to collapse into new stars. The spiral arms also play a crucial role in regulating the flow of material throughout the galaxy. As gas clouds move through the disk, they encounter the arms and slow down due to the increased density. This process helps maintain the arm structure and ensures a continuous cycle of star formation. Although individual stars do not remain in the arms permanently, their journeys through these regions shape their development. Many stars are born in the arms and then drift outward or inward as they age, leaving behind the bright nurseries that once marked their birthplaces. The spacing of the spiral arms is another important feature. Observations indicate that Andromeda's arms are more widely separated than those in the Milky Way, which may reflect differences in mass distribution, rotation speed, or past interactions. The precise spacing and symmetry of spiral arms depend on complex gravitational resonances within the galaxy, influenced by the central bar, the thickness of the disk, and the unseen distribution of dark matter. Andromeda's arms reveal much about its internal dynamics. The pattern of rotation is not uniform. Stars closer to the center orbit faster, while those farther out orbit more slowly. The density waves that form the spiral arms move at a different speed than the stars themselves. As a result, the arms continually shift and evolve, slowly changing shape over time, even as they retain their overall spiral appearance. Despite the elegance of Andromeda's spiral structure, it is not a perfect pinwheel, but a living, breathing formation. It bears the scars of ancient mergers, the traces of ongoing star formation, and the quiet influence of dark matter shaping its motion. The arms are both the skeleton and the heartbeat of the galaxy's vast luminous pathways, through which stars are born, evolve, and drift across cosmic time. Scattered throughout the vast halo of the Andromeda Galaxy lies one of its most remarkable and ancient populations, its globular clusters. These dense, spherical swarms of stars are among the oldest surviving structures in the universe, forming long before Andromeda took on its present spiral shape. Andromeda contains more than 450 known globular clusters, far more than the Milky Way's, roughly 150, making it one of the richest globular cluster systems in the local group. Each of these clusters is a self-contained world, holding hundreds of thousands of stars packed into a region sometimes only a few dozen light-years across. The sheer number and variety of these clusters reveal a deep and complex history etched into the galaxy's past. Globular clusters are ancient by nature. Many within Andromeda formed more than 12 billion years ago, when the universe itself was still in its infancy. Their stars are typically old, metal-poor, and stable, having survived countless cosmic changes without dispersing. The density of stars within a globular cluster is so high that the night sky from a planet inside one, if such a planet existed, would be filled with hundreds of thousands of bright suns, glowing so intensely that darkness might never truly fall. The distribution of Andromeda's globular clusters provides important insight into the galaxy's evolution. They are not confined to the disk, but are spread widely throughout the halo, some orbiting far beyond the visible edges of the galaxy. Their orbits vary drastically. Some follow tight circular paths, while others swing through the halo on long, elongated loops. These varied trajectories suggest that many clusters were not born in Andromeda at all, but were acquired from dwarf galaxies that were absorbed by the larger spiral over billions of years. Evidence for this comes from the chemical composition of the clusters. Some globular clusters in Andromeda have distinct metallicities, or stellar signatures, that mark them as foreign in origin, matching those found in known dwarf galaxies rather than in Andromeda itself. As these smaller galaxies were torn apart, their central clusters often survived the destruction and were left to orbit the larger galaxy as relics of ancient mergers. Andromeda's richest and most massive globular cluster, known as G1 or Male 2, is one of the brightest globular clusters in the entire local group. It is so large and massive that some astronomers believe it may once have been the core of a dwarf galaxy stripped of its outer stars. G1 contains millions of stars and shows evidence of multiple generations of star formation, a trait unusual for typical globular clusters, but consistent with the idea that it began life as a small galaxy. The study of Andromeda's globular clusters has also been essential for refining our understanding of distance measurement. By comparing their brightness and structure to those of similar clusters in the Milky Way, astronomers were able to calculate Andromeda's distance with increasing precision, helping to establish the scale of the universe. Globular clusters also serve as reliable tracers of dark matter. Because they orbit the galaxy at great distances, their movements reveal the gravitational field far beyond the visible disk. These motions show that Andromeda's dark matter halo extends to enormous sizes, with mass far exceeding what can be directly observed. In addition to their scientific value, globular clusters are windows into the earliest eras of galactic evolution. They formed at a time when heavy elements were scarce, long before supernovae had enriched the universe. Their stars shine with the chemical simplicity of the early cosmos, offering astronomers a glimpse into conditions that existed not long after the Big Bang. In the Andromeda Galaxy, globular clusters are more than ancient ornaments scattered across the halo. They are fossils of cosmic history. Each cluster carries the memory of a different time and place, some born within Andromeda, others carried in from galaxies long since lost. Together, they create a glittering, spherical archive floating around the spiral giant, preserving stories billions of years old as they continue their slow, majestic orbits through the darkness of intergalactic space. Across the Andromeda Galaxy's sprawling disk and far-reaching halo, countless planetary systems are likely to exist, each one orbiting its own star and shaped by its own history. While we cannot directly observe most of these systems, the laws of cosmic evolution strongly suggest that planets are abundant throughout Andromeda. Given that the galaxy contains roughly 1 trillion stars, even conservative estimates indicate that tens or hundreds of billions of planets may populate its expanse. Some of these worlds may be barren and icy, others scorching hot, and many more quietly orbit within zones where liquid water and life-supporting conditions might be possible. Our understanding of planetary formation comes from observing other galaxies, studying the Milky Way, and applying universal physical principles. Stars form from collapsing clouds of gas and dust, and as they ignite, the leftover material naturally flattens into a rotating disk. From this disk, particles collide and grow into planetesimals, which merge to form planets. This process is not unique to the Milky Way. It is a fundamental mechanism operating throughout the universe wherever stars are born. Andromeda, with its vast population of stars at various stages of evolution, must host countless such disks and newly formed planetary systems. The types of planets found in Andromeda would vary widely depending on the region of the galaxy. Near the bright, dense spiral arms, young stars and their surrounding disks may give rise to hot gas giants, rocky terrestrial planets, or tightly packed systems orbiting close to their hosts. These regions are rich in heavy elements, a necessary ingredient for building planets. Massive stars that eventually explode as supernovae enrich the interstellar medium with metals, allowing subsequent generations of stars to form more complex planetary systems. In the inner disk of Andromeda, where star formation was vigorous in earlier epochs, many older stars likely host ancient planetary systems. Some of these planets might have survived billions of years of cosmic evolution. Their surfaces could be shaped by repeated asteroid impacts, stellar radiation, or long-term climate variations driven by their stars' changing brightness. In contrast, The outer disk and halo contain stars that are older and more metal-poor. While planetary systems can still form in these regions, the planets may be smaller, simpler, and less diverse. Earth-like planets are more likely to emerge around stars with higher metal content, making the inner regions of Andromeda prime locations for such worlds. One particularly intriguing class of planets in Andromeda would be those orbiting, low-mass red dwarf stars, which make up the majority of the galaxy's stellar population. These stars burn slowly and steadily, offering long-lasting environments where life, if it arises, could have immense amounts of time to evolve. Planets around red dwarfs may face challenges such as strong stellar flares, but they remain some of the most common potential homes for habitability. Andromeda may also host countless rogue planets' worlds without a parent star drifting silently through the galaxy's halo. These planets could have been ejected from their systems during close encounters or gravitational disruptions. Though cold and dark, they may retain internal heat from their formation or from radioactive elements within their cores. Such planets are difficult to detect, but are expected to exist in enormous numbers. Another layer of complexity comes from Andromeda's history of mergers. When galaxies collide, gravitational forces can destabilize planetary systems, altering orbits or ejecting planets altogether. Some planets may have been torn from their stars during Andromeda's past interactions with dwarf galaxies, cast into new orbits around different stars, or sent wandering through interstellar space. The chemical diversity of Andromeda's stars also suggests that the galaxy contains worlds with widely varying compositions. Some might have surfaces rich in carbon or silicon, while others could be dominated by water ice, metals, or exotic minerals. The variety of environments would be immense, shaped by the galaxy's dynamic evolution. While we may never directly observe most of these planets, the physics of star and planet formation combined with the enormous scale of Andromeda leaves little doubt. The galaxy is teeming with worlds, from scorching super-Earths to icy giants, from habitable orbiters to lonely interstellar wanderers. Andromeda's planetary systems form a vast, unseen cosmos within a galaxy already rich in wonder. Surrounding the bright disk of the Andromeda Galaxy is one of its most captivating and revealing features, an enormous network of stellar streams and tidal debris, the faint remnants of smaller galaxies that Andromeda tore apart over billions of years. These streams trace ghostly arcs around the galaxy, forming loops, shells, and rivers of stars that stretch across hundreds of thousands of light years. They are among the clearest and most beautiful pieces of evidence for Andromeda's long history of galactic cannibalism. When a small galaxy strays too close to a massive one like Andromeda, the difference in gravitational forces between its near and far sides begins to tear it apart. Stars are peeled away, forming long trails that wrap around the larger galaxy. Over time, these trails stretch further, fade in brightness, and eventually blend into the halo, yet their shapes remain readable for billions of years like ancient scars. Andromeda contains many such structures, far more than originally expected. Deep surveys have revealed a vast, intricate halo filled with overlapping streams. Some appear as thin, graceful loops, others form wide, diffuse clouds. Each one is a fossil record of a past collision. One of the most famous of these structures is the giant stellar stream, a sweeping luminous ribbon that extends far beyond Andromeda's disk. It is composed of stars once belonging to a dwarf galaxy that merged with Andromeda roughly 2 billion years ago. The stream wraps around the galaxy in a nearly complete orbit, its stars moving along a path that reconstructs the gravitational shape of Andromeda's dark matter halo. Astronomers believe this dwarf galaxy plunged deep into Andromeda's core, was torn apart, and left behind the enormous stream that we now observe. Several smaller streams crisscross the halo as well. These include shells of stars that resemble ripples in a pond, spherical or crescent-shaped features left behind when a disrupted satellite galaxy shed material in bursts. These shells form when the cores of dwarf galaxies make repeated passes through Andromeda, losing stars with each orbit. The stars settle into patterns dictated by gravity, creating these elegant, layered formations. The presence of so many streams suggests that Andromeda's past was marked by frequent and sometimes violent interactions. Galaxies grow by absorbing smaller ones, and Andromeda appears to have been particularly active in this cosmic harvesting. The variety of streams indicates that some mergers were recent and dramatic, while others occurred long ago and have nearly faded into the background of the halo. The chemical composition of the stars within these streams provides further clues. Some streams contain stars with very low metallicities, indicating they originated from primitive dwarf galaxies formed early in the universe. Others are richer in heavy elements, suggesting they came from later, more evolved systems. These variations help astronomers reconstruct when each merger happened and what types of galaxies were involved. The motions of stars within these streams are equally informative. By tracking their orbits, scientists can map the distribution of Andromeda's dark matter. Streams act as test particles moving through the galaxy's gravitational field. Their paths bend and twist according to the invisible mass around them, allowing researchers to infer the shape and density of Andromeda's dark matter halo. Beyond their scientific value, the streams are visually stunning when observed in deep images. They form delicate filaments of light against the dark halo, like stardust trails left behind from lost worlds. Though they are extremely faint, often thousands of times dimmer than the main disk, their subtle beauty highlights the complexity of galactic evolution. In a broader sense, the stellar streams around Andromeda reveal a profound truth about galaxy formation. Nothing in the cosmos remains untouched forever. Large galaxies grow by incorporating smaller ones, and the remnants of these mergers remain written across the sky. The streams surrounding Andromeda are the memories of galaxies long gone, preserved in elegant winding arcs that continue to orbit in silence. They remind us that Andromeda is not just a static structure, but a dynamic, living system shaped by billions of years of encounters, and that even now, the galaxy's halo still whispers the stories of the stars that once belonged to other worlds. The chemical makeup of the stars within the Andromeda Galaxy acts like a detailed historical record, preserving clues about how the galaxy formed, evolved, and merged with countless smaller systems over billions of years. Every star carries a unique chemical fingerprint imprinted at birth, an elemental recipe that reflects the environment in which it formed. By studying these chemical signatures, astronomers can trace Andromeda's past in extraordinary detail, uncovering its major epochs of growth, its mergers, and even the characteristics of long-vanished galaxies it once absorbed. One of the clearest markers of stellar age and origin is metallicity, the abundance of elements heavier than hydrogen and helium. In astronomy, metals include oxygen, carbon, iron, and all heavier elements. Stars with very low metallicity typically formed early in the universe, before multiple generations of supernovae had enriched the cosmic gas supply. Stars with higher metallicity formed later, when the interstellar medium contained more heavy elements produced by previous generations of stars. In Andromeda, metallicity varies dramatically depending on where one looks. Near the galaxy's center, stars tend to be more metal-rich, indicating that they formed in a region where gas had been repeatedly recycled and enriched. The dense inner bulge has undergone numerous cycles of star birth and death, each one adding more heavy elements to the environment. This high degree of enrichment suggests that Andromeda's core experienced intense periods of star formation, likely triggered by mergers and interactions early in the galaxy's life. Moving outward into the disk, metallicities decrease but remain relatively high compared to similar regions of the Milky Way. This suggests that Andromeda has been more efficient at enriching its gas, or has undergone more past mergers, each one stirring the disk and distributing heavy elements through its stars and gas. The spiral arms, where star formation still occurs, contain younger stars with a broad range of metallicities, reflecting the mixed nature of the gas feeding those stellar nurseries. In the halo far beyond the main disk, the story becomes far more complex. The halo contains some of the oldest and most metal-poor stars in the entire galaxy, many of them relics from small primitive dwarf galaxies Andromeda destroyed long ago. These ancient halo stars often show extremely low iron content, but enhanced levels of certain lighter elements, marking them as products of early massive stars that enrich their surroundings in very particular ways. Their composition gives astronomers one of the clearest windows into the chemical conditions of the early universe. But not all halo stars are metal poor. Some have surprisingly high metallicities, far too high to have formed in such remote regions. These stars likely originated in dwarf galaxies that Andromeda absorbed more recently, galaxies that had already undergone substantial chemical enrichment before being shredded by tidal forces. The halo is therefore a mosaic of populations, some stars formed within Andromeda itself, while others were brought in during various merger events. Chemical tagging analyzing detailed elemental patterns in stars helps astronomers group stars that share a common origin. Stars that form together in a dwarf galaxy share a specific chemical combination. When these stars appear scattered across the halo in tidal streams, they reveal the fate of their long-lost parent systems. In this way, chemistry becomes a tool for galactic archaeology, allowing scientists to reconstruct Andromeda's merger history even when visual evidence has faded. The chemical makeup of Andromeda's stars also hints at differences between Andromeda and the Milky Way. Studies suggest that Andromeda experienced more recent mergers and more vigorous bursts of star formation, leaving it with a wider variety of chemical signatures. Its halo is richer and more complex, signifying more collisions. Andromeda's stars therefore paint a picture of a galaxy that grew aggressively, consuming many smaller companions and mixing their stellar populations into its own. In essence, the chemistry of Andromeda's stars is a cosmic archive. Each star carries the memory of its birthplace, whether it was born deep in the enriched heart of the galaxy, along a spiral arm, or in a small dwarf galaxy torn apart and scattered. Combined, these chemical fingerprints reveal a galaxy shaped by constant change, enriched by stellar generations, and built from the remnants of countless smaller worlds. The Andromeda Galaxy is not only a majestic spiral of stars and dust, but also a powerful source of high-energy phenomena. Surrounding the visible disk and extending far into intergalactic space is a vast halo of hot gas, so diffuse that it cannot be seen in visible light, yet so energetic that it glows in ultraviolet and X-ray wavelengths. This halo forms an immense cocoon around the galaxy, stretching hundreds of thousands of light years and holding a mass of gas comparable to, or even greater than, the entire stellar content of Andromeda. Its existence reveals the invisible side of galactic evolution, shaped by supernova explosions, cosmic winds, and ancient collisions that heated the gas to millions of degrees. One of the driving forces behind Andromeda's high-energy environment is its population of supernova remnants, the expanding shells of gas left behind when massive stars explode. Each supernova releases an enormous amount of energy, heating surrounding gas, accelerating particles to near-light speed, and enriching the galaxy with heavy elements. Over billions of years, Andromeda has hosted countless supernova, each contributing to the hot halo. These remnants emit strongly in X-ray wavelengths, revealing shock fronts, tangled magnetic fields, and pockets of superheated plasma. The brightest of these remnants offer insight into the deaths of massive stars and the turbulent shaping of the interstellar medium. In addition to supernovae, Andromeda hosts numerous X-ray binary systems pairs of stars, in which one member is a neutron star or black hole pulling material from its companion. As the stolen gas spirals inward, it heats up to extreme temperatures, emitting bursts of X-rays that flicker and pulse over time. These systems act like cosmic lighthouses, flashing signals that reveal the presence of compact objects otherwise invisible to telescopes. Some of the most powerful X-ray sources in Andromeda rival those found in the Milky Way, offering a rich field of study for understanding how stars evolve after exhausting their nuclear fuel. The galaxy's central region also emits high-energy radiation. Although Andromeda's supermassive black hole is currently quiet compared to active galactic nuclei, it still generates faint X-ray emission from hot gas that drifts toward the event horizon. This weak but persistent glow hints at past epochs when the black hole may have been far more active, possibly launching jets or outflows that carried energy deep into the halo. Some astronomers believe that relic shock waves or cavities in the surrounding gas could be remnants of these ancient episodes. Andromeda's halo itself is a complex environment, where temperatures reach into the millions of degrees. Although extremely thin, this gas fills an enormous volume, forming a kind of energetic atmosphere that envelopes the entire galaxy. When observed in ultraviolet light, the halo reveals clouds of ionized oxygen and other elements drifting far from the disk. These clouds move in patterns that hint at past interactions, such as dwarf galaxies plunging through the halo or gas being stripped from satellites by Andromeda's gravity. The halo also acts as a reservoir for future star formation. Over long timescales, the hot gas may cool and fall back into the disk, replenishing the material needed to form new stars. At the same time, the halo slowly absorbs gas blown outward by supernovae and stellar winds, creating a circulation cycle that ties together the inner and outer regions of the galaxy. Another component of Andromeda's high-energy activity is cosmic rays, high-speed particles accelerated by supernova shocks, magnetic turbulence, and remnants of past mergers. These particles streak through the galaxy, interacting with gas and magnetic fields to produce faint gamma-ray and radio emissions. Although difficult to detect directly, their presence influences the temperature, pressure, and chemical evolution of the interstellar medium. Together, the hot gas, X-ray sources, and energetic particles paint a vivid picture of Andromeda as a galaxy alive with invisible activity. While its spiral arms and bright stars dominate visible images, the high-energy universe reveals a deeper, turbulent structure shaped by violent events and extreme environments. It is a reminder that galaxies are not quiet islands of stars, but dynamic systems where creation and destruction coexist, each contributing to the ongoing evolution of the cosmos. Threaded through the vast expanse of the Andromeda Galaxy is an intricate network of magnetic fields, silent, invisible structures that weave through the galaxy's disk, halo, and interstellar medium. Though they cannot be seen with the naked eye, these magnetic fields shape the flow of gas, guide charged particles, influence star formation, and reveal the hidden skeleton of the galaxy. Andromeda's magnetic field is remarkably well organized for a galaxy its size, forming coherent patterns that extend across tens of thousands of light years. Radio observations show that the field lines form swirling structures aligned with the spiral arms, tracing the paths of gas and dust that wind around the galaxy. These fields act like rails along which charged particles travel, shaping cosmic rays into arcs and filaments that glow when observed in radio wavelengths. In the densest regions of the spiral arms, where star formation is most active, the magnetic fields intensify. Massive stars produce strong stellar winds and supernova explosions that compress and twist the surrounding gas. These processes amplify the magnetic fields, creating bright, polarized radio emissions that outline the star-forming regions. The fields guide the movement of material within molecular clouds, slowing or speeding up collapse in different directions, and thereby influencing how stars and planetary systems emerge. Without magnetic fields, star formation in Andromeda would look very different, more chaotic, faster in some places, slower in others. The central region of Andromeda also contains intricate magnetic structures. Near the galactic bar and core, the fields appear more turbulent, shaped by gas flowing inward, and by the gravitational influence of the supermassive black hole. Though the black hole is currently quiet, the region around it shows signs of twisted and compressed magnetic lines, which may be relics of past activity when the core was more energetic. If Andromeda's black hole once launched jets or outflows, those events would have stretched and folded the magnetic fields, leaving behind patterns still detectable today. Beyond the visible disk, Andromeda's magnetic field extends into the halo, where it becomes weaker and more irregular. Here, it takes the form of faint, tangled filaments carried by streams of hot gas and dust that escaped the disk long ago. These halo fields may be remnants of past mergers or interactions with satellite galaxies. As dwarf galaxies plunged into Andromeda's massive halo, their own magnetic structures likely merged with Andromeda's, adding to the complexity of the outer regions. Some of the halo's magnetic loops appear connected to the giant stellar streams that arc around the galaxy. If these streams originated from disrupted dwarf galaxies, their magnetic fields would have been stretched into long filaments as they were torn apart, forming another subtle signature of Andromeda's history of galactic cannibalism. Magnetic fields also play a crucial role in shaping Andromeda's cosmic ray environment. High-energy particles, produced mainly by supernova explosions, spiral along magnetic field lines rather than traveling straight through the galaxy. The fields trap and guide these particles, influencing where they heat gas, where they accumulate, and how long they remain in the galaxy before escaping into intergalactic space. This delicate interplay affects everything from the temperature of diffuse gas to the radiation environment experienced by stars and potential planetary systems. Another hidden structure revealed by magnetic mapping is the presence of large-scale magnetic bridges or threads that connect different parts of the disk. These threads may guide the flow of gas from the outer regions inward, subtly shaping the overall dynamics of the galaxy. They represent long-range coherence in the magnetic field, showing that Andromeda's field is not random, but shaped by rotation, density waves, and the overall structure of the galaxy. Although invisible, Andromeda's magnetic field is fundamental to understanding its unseen framework. It influences star formation, organizes cosmic ray motion, reveals the effects of past mergers, and permeates the halo with delicate interwoven patterns. These hidden structures remind us that galaxies are far more complex than their starlight alone suggests. Vast tapestries woven not only of matter and gravity, but also of magnetic energy stretching silently across cosmic space. Long before astronomers could measure the true scale of the universe, the Andromeda Galaxy played a crucial role in helping humanity understand the vastness of cosmic space. This breakthrough came from a special class of stars known as variable stars, particularly Cepheid variables and RR Lyrae stars, whose rhythmic changes in brightness act like cosmic beacons. These stars allow scientists to measure distances with remarkable precision, making them essential tools in reconstructing the size, structure, and history of the universe. Cepheid variables are massive, pulsating stars whose brightness rises and falls in a predictable cycle. The period of their pulsation, the time it takes for them to brighten and dim, is directly related to their intrinsic luminosity. This means that by observing how quickly a Cepheid brightens and fades, astronomers can determine how bright it truly is, compare that intrinsic brightness to how bright it appears from Earth, and calculate its distance. This relationship, discovered by Henrietta Swan-Leavitt in the early 20th century, became one of the most important tools in astronomy. When Edwin Hubble studied Andromeda in the 1920s, he identified several Cepheid variables in the galaxy's outer regions. By measuring their pulsation periods, he calculated their intrinsic brightness and compared it to their apparent brightness. The resulting distance over 1 million light-years was far larger than the size of the Milky Way, proving that Andromeda was an entirely separate galaxy. This discovery shattered the long-held belief that the Milky Way contained the entire universe and opened the door to the concept of a vast cosmos filled with countless galaxies. Other types of variable stars also play an important role in understanding Andromeda's structure. RR Lyrae stars, for instance, are older and less massive than Cepheid variables. They can be found in globular clusters and the halo, making them excellent tracers of ancient stellar populations. RR Lyrae stars have a consistent intrinsic brightness, allowing astronomers to use them as standard candles. By mapping their distribution, researchers can trace the shape, size, and density of Andromeda's outer halo. These stars have helped reveal the presence of stellar streams, remnants of dwarf galaxies absorbed long ago. In addition to helping measure distances, variable stars offer insights into Andromeda's stellar evolution. The metallicity of these stars, the amount of heavy elements they contain, reveals the chemical richness of different regions. Cepheids, for example, tend to be younger and more metal-rich, indicating areas with more recent star formation. RR Lyrae stars, being old and metal-poor, trace the earliest generations of stars. Their presence in Andromeda's halo suggests that the galaxy began forming stars very early in the universe's history. Modern tools such as the Hubble Space Telescope and the Gaia mission allow astronomers to study these variable stars with unprecedented accuracy. Gaia's precise measurements of stellar motion help determine how stars move within Andromeda's halo, providing clues about the galaxy's mass, dark matter distribution, and merger history. Cepheids and RR Lyrae stars also help refine models of cosmic expansion. Because they serve as distance anchors, they contribute to the calibration of the cosmic distance ladder, a system of overlapping techniques that allows astronomers to measure distances from nearby stars to distant galaxies. Without reliable variable stars in Andromeda, these measurements would be far less accurate. Today, variable stars continue to illuminate Andromeda's story. They show where star formation is occurring, where ancient stars reside, and how gas and dust have moved through the galaxy over time. They confirm that Andromeda is not just a swirl of stars, but a dynamic, evolving system shaped by billions of years of cosmic processes. Their rhythmic pulses echo across space, carrying information about distance, age, and composition. In many ways, variable stars are the clocks and compasses of the universe, guiding our understanding of space on the grandest scales. For thousands of years, the Andromeda Galaxy has been a silent companion in humanity's night sky, long before we understood its true nature. In ancient times, people saw it not as a galaxy, but as a faint, mysterious cloud, a soft blur just visible to the naked eye under dark skies. The Persian astronomer Abd al-Rahman al-Sufi was the first known observer to record it clearly, describing it in 964 CE as a little cloud in his Book of Fixed Stars. For centuries after that, Andromeda remained an ethereal curiosity, mentioned occasionally in star catalogues but never fully understood. It wasn't until the invention of the telescope that Andromeda began to reveal its structure. Early observers like Simon Marius in 1612 described it as a nebula, a term used at the time for any fuzzy, cloud-like object in the sky. Marius, observing through a primitive telescope, noted that it appeared like a glowing patch with no clear boundaries. Even through better telescopes of the 18th and 19th centuries, Andromeda continued to puzzle astronomers. Some believed it was a nebula within the Milky Way. Others suspected it might be something far more distant. As astronomical instruments improved, Andromeda became part of a growing debate about the nature of the universe. In the early 20th century, two prominent astronomers, Harlow Shapley and Heber Curtis, debated whether so-called spiral nebulae like Andromeda were part of the Milky Way or separate island universes. Their ideas clashed in what became known as the Great Debate of 1920. Shapley argued that the Milky Way was so large that all nebulae must belong to it. Curtis argued that the nebulae were external galaxies. The answer came a few years later, thanks to Edwin Hubble. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble identified Cepheid variable stars in Andromeda stars, whose predictable brightness allowed him to determine their distance. The result was revolutionary. Andromeda was far too distant to be part of the Milky Way. It was a galaxy in its own right, comparable in size to our own. Hubble's discovery transformed astronomy forever, proving for the first time that the universe was vast and filled with countless galaxies beyond the Milky Way. After Hubble's work, Andromeda became a cornerstone in the study of galactic structure. It offered astronomers a nearby example of a spiral galaxy, close enough to observe in detail but far enough to be studied as a whole. Through photography, spectroscopy and radio observations, scientists mapped its spiral arms, measured its rotation and studied its gas, dust and star populations. As technology advanced, Andromeda continued to play a key role. Infrared telescopes revealed its hidden dust lanes. X-ray observatories discovered binary star systems and hot gas. Advanced ground-based telescopes mapped the motions of its stars. And space telescopes like Hubble and Gaia provided some of the sharpest images ever taken of an external galaxy. Andromeda has also become a cultural icon. It appears in science books, documentaries and space art, often symbolizing the beauty and mystery of the universe. Its eventual collision with the Milky Way has captured the public imagination, inspiring both awe and curiosity about the far future. Throughout human history, Andromeda has been a beacon in the sky, a reminder of how small we are and how much there is to explore. From a faint smudge noted by ancient astronomers to a centerpiece of modern cosmology, the galaxy has shaped our understanding of the universe. Even today, it continues to teach us, serving as both a scientific treasure and a symbol of humanity's enduring fascination with the stars. In modern astronomy, the Andromeda Galaxy serves as one of the most important laboratories for understanding how large galaxies form, evolve, and interact with their environments. Because it is the closest giant spiral galaxy to the Milky Way, Andromeda provides an unparalleled opportunity to study the processes that shape galaxies like our own. It is far enough away to be seen as a complete system, yet close enough for telescopes to resolve individual stars, star clusters, and structural features with remarkable clarity. This unique combination makes Andromeda a cornerstone in contemporary scientific research. One of the key reasons Andromeda is so valuable to modern science is its role as a template for understanding spiral galaxies. Its structure spiral arms, central bar, bulge, halo, and extensive networks of dust and gas reveals how large galaxies organize themselves over billions of years. By comparing Andromeda to the Milky Way, astronomers can determine which features are typical and which may be unique to our galaxy. For example, Andromeda's slightly larger mass and more active merger history help scientists understand how differences in galactic evolution lead to variations in shape, star formation, and chemical composition. Andromeda is also a testing ground for cosmological theories, particularly those related to dark matter. Because its stars and globular clusters can be observed across great distances, Andromeda's rotation curve can be measured with exceptional precision. These measurements confirm the presence of a massive dark matter halo extending far beyond the visible disk. By studying the motions of stars and satellite galaxies, researchers can refine models of how dark matter is distributed and how it influences galactic evolution. The galaxy's extensive stellar streams remnants of smaller galaxies torn apart by Andromeda's gravity provide additional clues about the nature of dark matter. Their shapes and motions reveal how the galaxy's gravitational field is structured, allowing astronomers to map the invisible dark matter halo with increasing accuracy. Andromeda also helps scientists understand the life cycle of galaxies. Its star-forming regions show how gas clouds collapse to create new stars. Its older stellar populations reveal how galaxies age, and its halo preserves evidence from mergers that occurred billions of years ago. Observing the galaxy across different wavelengths, from radio waves to gamma rays, allows researchers to build a comprehensive picture of its structure and activity. In ultraviolet images, regions of intense star formation blaze brightly. Infrared observations penetrate dust to reveal hidden star clusters and nebulae. X-ray and gamma-ray telescopes detect black holes, neutron stars, and hot gas that would otherwise remain invisible. One of the most significant aspects of modern research involving Andromeda is its future collision with the Milky Way. By measuring Andromeda's proper motion, the tiny sideways shift of the galaxy across the sky, scientists are able to model the upcoming merger with unprecedented precision. These simulations reveal how the two galaxies will interact, how their stars will move, and what the resulting galaxy will eventually look like. This research not only predicts our cosmic future, but also helps astronomers understand how giant elliptical galaxies form elsewhere in the universe. The Andromeda Galaxy also plays a central role in calibrating the cosmic distance ladder. Its Cepheid variables, RR Lyrae stars, and Type Ia supernovae provide multiple independent methods for measuring distances, making it a crucial anchor in determining the scale of the universe. Each new observation, whether from Hubble, Gaia, the James Webb Space Telescope, or large ground-based observatories, adds more precision to these measurements. As one of the most studied galaxies in the universe, Andromeda continues to reveal new surprises. Discoveries such as the plane of dwarf galaxies, the complex shape of its halo, its extended gas envelope, and unusual central structures challenge existing theories and push scientists to refine their understanding. Andromeda is not merely a neighboring galaxy, it is a cosmic guide, a vast natural laboratory that allows astronomers to explore the fundamental processes shaping galaxies across the universe. Through its stars, streams, clusters, and dark matter, it continues to illuminate the workings of the cosmos, helping us piece together the story of how galaxies grow, evolve, and interact on the grandest scales imaginable. Far into the future, after the Milky Way and the Andromeda Galaxy complete their long gravitational dance and finally merge, a new galaxy will be born, an enormous elliptical or lenticular system often referred to as Milkdromeda or Milkomeda. This future galaxy will not simply be a blend of the two spirals, but a transformed structure reshaped by billions of years of merging, star formation, and gravitational interactions. To imagine Milkdromeda is to envision the cosmic future of our entire stellar neighborhood, a galaxy fundamentally different from either of its predecessors. In the early stages of the merger, both galaxies will stretch and distort, their spiral arms flung into long tidal tails that arc through space. These ephemeral structures will eventually fade, but in the process they will seed the future galaxy with stars flung far into the halo. After several passes, the cores of the Milky Way and Andromeda will finally settle into a single, denser center. The violent gravitational interactions will dissolve the ordered spiral patterns, replacing them with a more rounded, smooth distribution of stars. By the time the merger stabilizes, Milkdromeda will resemble the giant elliptical galaxies seen in galaxy clusters today, massive, bright, and lacking the prominent spiral arms that once defined its ancestors. Star formation in the new galaxy will undergo dramatic changes. During the merger, gas clouds from both galaxies will collide and compress, triggering a temporary but spectacular starburst phase. For hundreds of millions of years, new stars will ignite at rates far exceeding those seen in either galaxy today. Clusters of brilliant, short-lived stars will illuminate the merging system, their intense radiation and eventual supernova shaping the surrounding gas. But this frenzy of creation will not last. Once the available gas is consumed or heated beyond the point of collapse, star formation will gradually decline. Over billions of years, Milkdromeda will transition into a quieter, older galaxy, populated mainly by long-lived stars that shine steadily without replenishment. The central region of Milkdromeda will be a place of particular interest. As the supermassive black holes from the Milky Way and Andromeda drift closer together, they will enter a tight orbital dance, radiating gravitational waves that slowly drain their orbital energy. Eventually, the two black holes will merge into a single, even more massive central black hole, possibly tens or hundreds of millions of times the mass of the Sun. This event will release an enormous burst of gravitational radiation that ripples across the universe, though no life is likely to remain close enough to witness it. As the new galaxy stabilizes, its dark matter halos will blend into a single, enormous envelope, reshaping the gravitational landscape of the local group. Many of the smaller satellite galaxies will be drawn inward, gradually merging with Milkdromeda as well. Others may remain as distant companions, orbiting the newly formed giant for trillions of years. The Triangulum Galaxy, M33, depending on its exact trajectory, may either join the merger early or remain as a long-term orbital partner. The night skies of any surviving planetary systems will change dramatically. Instead of a thin band of stars like the Milky Way's current disk, future inhabitants would see a dense, glowing core filling a large portion of the sky, surrounded by a sprawling halo of stars. The galaxy would appear as a massive, luminous sphere rather than a delicate spiral. Over the longest timescales, Milkdromeda will continue to evolve. Stars will age and fade into white dwarfs, neutron stars, and black holes. New star formation will dwindle to almost nothing. The galaxy will slowly become redder and dimmer, its brilliant starburst past replaced by a calm population of ancient suns. Yet the galaxy will remain gravitationally bound, drifting through space as part of an even larger structure that will form when the local group merges with nearby galaxy groups in the endless expansion of the universe. Ultimately, Milkdromeda represents not an end but a transformation, a new chapter in the cosmic story of two great spirals that once drifted through space side by side. Through gravity, time, and the relentless process of galactic evolution, they will create something larger and more magnificent than either galaxy could be alone. As we drift toward the end of our journey through the Andromeda Galaxy, it becomes clear that this colossal, shimmering structure is far more than a distant patch of light in the night sky. It is a vast, multi-layered story unfolding across billions of years, a story of creation and destruction, of stars igniting and fading, of galaxies merging, stretching and transforming as time marches on. In its glowing disk, in its sprawling halo, and in the countless worlds it surely harbours, Andromeda stands as a silent testament to the beauty and complexity of the universe. When we look at Andromeda from Earth, we see only a faint blur, a whisper of cosmic light, barely bright enough to rise above the darkness. Yet hidden within that faint glow is the combined radiance of 1 trillion stars, each one shining its own history into the vastness. Some of those stars were born mere millions of years ago, still wrapped in the last wisps of their birth clouds. Others ignited more than 10 billion years ago, carrying with them the signature of a universe far younger than the one we live in now. They are the living archive of a galaxy that has grown through collisions, interactions, and the ceaseless pull of gravity. The calm appearance of Andromeda in the sky might suggest permanence, but in reality, it is a galaxy in motion, a structure that changes slowly but continuously. Its stars drift along their orbits, its spiral arms reshape themselves over hundreds of millions of years, its halo absorbs the remnants of smaller galaxies, and its future is already entwined with our own, destined to merge with the Milky Way in an elegant cosmic ballet billions of years from now. Even now, deep within its core, stars swirl around a supermassive black hole in tight, overlapping loops, moving through a region where time and gravity bend in extraordinary ways. Farther out, clusters of ancient stars orbit like distant lanterns, relics of the earliest days of galaxy formation. Stellar streams curl across the halo, marking the paths of galaxies long since torn apart. Dust lanes thread through the spiral arms, shaping nebulae and star-forming regions that act as the galaxy's nurseries. And between the stars, magnetic fields, hot gas, and dark matter weave an invisible framework that holds the entire system together. Andromeda is also a reminder of how far humanity has come in its understanding of the universe. For most of history, it was nothing more than a curious smudge, something seen but not understood. It took centuries of observation, the invention of the telescope, and the insights of brilliant scientists for us to recognize Andromeda as a galaxy beyond our own. Its discovery transformed our sense of scale and expanded our understanding of the cosmos from a small, star-filled dome into an ocean of galaxies stretching across unimaginable distances. Standing beneath the night sky, knowing that Andromeda approaches us slowly yet inevitably, we become aware of our place in a universe shaped by forces both grand and gentle. The same gravity that binds galaxies together also binds planets to stars and holds us firmly on our world. The same stars that shine in Andromeda follow the same physical laws as those in the Milky Way. In this way, Andromeda is not merely a distant object, it is a mirror of the cosmic processes that shaped our own home. As we conclude this exploration, we are left with a sense of awe. The Andromeda Galaxy is a quiet beacon in the sky, a silent guardian of cosmic history, and a future partner in a magnificent merger that will reshape our corner of the universe. It invites us to look upward, to wonder, and to remember that even the faintest glow in the night sky may hold stories more vast and beautiful than we can imagine.